We're from the 10th group, the last group of Introduction to Real Analysis 1 will present about the Cauchy Criterion. Group 10 consists of 3 people: Vena Agustina, Laela Ainur Rokhmah, and Bernadinus Estu Untara. Let's start now.
Okay, let's start. The monotone convergence theorem is extraordinarily useful and important, but it has the significant drawback that it applies only to the sequences that are monotone. It is important for us to have a condition implying the convergence of a sequence that does not require us to know the value of the limit in advance, and is not restrict to monotone sequence. The Cauchy criterion, which will be established in this section, is such a condition. Now let's talk about the definition. A sequence X equal to Xn sequence Xn of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0 there exists a natural number h epsilon such that for all natural numbers n, m greater than or equal to h epsilon, the terms xn, xm satisfy the absolute value xn minus xm less than epsilon. The significance of the concept of Cauchy sequence lies in the main theorem of this section, which asserts that a sequence of real numbers is convergent if and only if it is a Cauchy sequence. This will give us a method of proving a sequence converges without knowing the limit of the sequence. However, we will first highlight the definition of Cauchy sequence with the following example. Okay, next. This sequence, 1 over n, is a Cauchy sequence. If epsilon greater than 0 is given, we choose a natural number h equal to h epsilon such that h greater than 2 over epsilon. Then, if m, n greater or equal to h, we have 1 over n 1 over n less than or equal to 1 over h less than epsilon over 2. And similarly, 1 over m less than epsilon over 2. Therefore, it follows that if m, n greater or equal to h, then absolute value of 1 over n minus 1 over m less than or equal to 1 over n plus 1 over m less than epsilon over 2 plus epsilon over 2 equals to epsilon. Since epsilon greater than 0 is arbitrary, we conclude that the sequence 1 over n is a Cauchy sequence. Now, let's go into the second example. The sequence 1 plus negative 1 over n is not a Cauchy sequence. The negation of the definition of the Cauchy sequence is there exists epsilon 0 greater than 0 such that for every h there exists at least one n greater than h and at least one m greater than h such that the absolute value of xn minus xm greater than or equal to epsilon 0. Okay, for the terms xn equal to 1 plus negative 1 over n, I mean power n, we observe that if n is even, then xn equals to 2 and xn plus 1 equals to 0. If we take epsilon 0 equals to 2, then for any h, we can choose an even number n greater than h and let m equal to n plus 1 to get absolute value of xn minus xn plus 1 equals to 2, that is epsilon 0. we conclude that Xn is not a Cauchy sequence. We emphasize that to prove a sequence Xn is a Cauchy sequence, we may not assume a relationship between m and n. Since the required inequality, the absolute value of xn minus xm less than epsilon, must hold for all n, m greater than or equal to h epsilon. But to prove a sequence is not a Cauchy sequence, we may specify a relation between n and m as long as arbitrarily large value of n and m can be chosen so that the absolute value of xn minus xm greater than or equal to epsilon 0, or as you can say the negation. Our goal is to show that the Cauchy sequences are precisely the convergent sequence. First, we will prove that the convergent sequence is a Cauchy sequence. Okay, lemma 3.5.3. If x equal to the sequence xn is a convergent sequence of real numbers, then x is a Cauchy sequence. We do proof if x equals to lim big X, then given epsilon greater than 0, there's a natural number k epsilon over 2 such that if n greater than or equal to k epsilon over 2, then the absolute value of xn minus x less than epsilon over 2. Thus, if h epsilon is equal to k epsilon over 2, and if n, m greater than or equal to h epsilon, then we have absolute value of xn minus xm equal to absolute value of xn minus x plus x minus xm less than or equal to the absolute value of xn minus x plus absolute value of xm minus x less than epsilon over 2 plus epsilon over 2. Here we got epsilon. Since epsilon greater than 0 is arbitrary, it follows that sequence xn is a Cauchy sequence. It can prove. Okay, next we go to the lemma 3.5.4. A Cauchy sequence of real numbers is bounded. Let x big X equal to sequence xn be a Cauchy sequence and let epsilon equal to 1. If h equal to h1 and n greater than or equal to h, then x, the absolute value of xn minus xh less than 1. Hence, by the triangle inequality, we have that the absolute value of xn less than or equal to the absolute value of xh plus 1 for all n greater than or equal to h. If we set, we can see m equal to supremum, the absolute value of x1, comma absolute value of x2, blah blah blah, until the absolute value of x h minus 1, comma the absolute value of xh plus 1. Then it follows that the absolute value of xn less than or equal to m for all n, the element of natural number. That it has been proved. Okay, next we go to the Cauchy convergence criterion 3.5.5. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. Okay, proof. We have seen in lemma 3.5.3 that a convergent sequence is a Cauchy sequence. Conversely, let x big X equals to sequence xn be a Cauchy sequence. We will show that x is convergent to some real number. First, we observe from lemma 3.5.4 that sequence big X is bounded. Therefore, by the Bolzano-Weierstrass theorem 3.4.8 that has been represented by previous group, there is a subsequence x prime equals to sequence x and k of big X that converts to some real number x star. We shall complete the proof by showing that x converts to x star. Since the big X equal to sequence xn is a Cauchy sequence, given epsilon greater than 0, there is a natural number h epsilon over 2 such that if n, m greater than or equal to h epsilon over 2, then we can see absolute value of xn minus xm less than epsilon over 2. Since the subsequent x star equals to sequence x and k converts to x star, there is a natural number k greater than or equal to h epsilon over 2 belonging to the set n1 and 2 blah 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 such that absolute value of xk minus x star less than epsilon over 2. Since k greater than or equal to h epsilon over 2, it follows from the 1 we can see absolute value xn minus xm less than epsilon over 2 with m equals to k, that absolute value of xn minus xk less than epsilon over 2 for n greater than or equal to h epsilon over 2. Therefore, if n greater than or equal to h epsilon over 2, we have absolute value of xn minus x star equals to absolute value of xn minus xk plus xk minus x star less than or equal to the absolute value of xn minus xk plus absolute value of xk minus x star less than or equal to epsilon over 2 plus epsilon over 2. We get equal to epsilon. Since epsilon greater than 0 is arbitrary, we infer that limit of sequence xn is equal to x star. Therefore, we can conclude that the sequence x is convergent.
And then next is example 3.5.6. Let x equal xn be defined by x1 equal 1, x2 equal 2, and xn equal a half times xn minus 2 plus xn minus 1 for n greater than 2. It can be shown by induction that 1 less than or equal to xn less than or equal to 2 for all n element n. Some calculation shows that the sequence x is not monotone. However, since the terms are formed by averaging, it is readily seen that absolute value xn minus xn plus 1 equal 1 over 2 power n minus 1 for n element n. Prove this by induction. Thus, if m greater than n, we may employ the triangle inequality to obtain absolute value xn minus xm less than or equal to absolute value xn minus xn plus 1 plus absolute value xn plus 1 minus xn plus 2 plus until absolute value sm minus 1 minus xm equal 1 over 2 power n minus 1 plus 1 over 2 power n plus until 1 over 2 power m minus 2 equal 1 over 2 power n minus 1 times 1 plus a half plus until 1 over 2 power m minus n minus 1 less than 1 over 2 power n minus 2. Therefore, given epsilon greater than 0, if n is chosen so large that 1 over 2 power n less than epsilon over 4, and if m greater than or equal to n, then it follows the absolute value xn minus xm less than epsilon. Therefore, x is Cauchy sequence in R. By the Cauchy criterion 3.5.5, we infer that the sequence x converges to a number x. To evaluate the limit x, we might first pass to the limit in the rule of definition xn equal a half times xn minus 1 plus xn minus 2. To conclude that x must satisfy the relation x equal a half times x plus x, which is true but not informative. Hence, we must try something else. Since x converges to x, so does the subsequent x prime with odd indices. By induction, the reader can establish that C1.2.4f. So, as 2n plus 1 equal 1 plus a half plus 1 over 2 power 3 plus until 1 over 2 power 2n minus 1 equal 1 plus 2 over 3 times 1 minus 1 over 4 power n. It follows from this that x equal limit x prime equal 1 plus 2 over 3 equal 5 over 3. The next example, let y equal yn be the sequence of real numbers given by y1 equal 1 over 1 factorial, y2 equal 1 over 1 factorial minus 1 over 2 factorial, until yn equal 1 over 1 factorial minus 1 over 2 factorial plus until minus 1 power m plus 1 over n factorial. Clearly, y is not a monotone sequence. However, if m greater than n, then ym minus yn equal minus 1 power n plus 2 over n plus 1 factorial plus minus 1 power n plus 3 over n plus 2 factorial plus until minus 1 power m plus 1 over m factorial. Since 2 power r minus 1 less than or equal r factorial C1.2.4a, it follows that if m greater than n, then absolute value ym minus yn less than or equal to 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus until 1 over m factorial less than or equal 1 over 2 power n plus 1 over 2 power n plus 1 plus until 1 over 2 power n minus 1 less than 1 over 2 power n minus 1. Therefore, it follows that yn is Cauchy sequence. Hence, it converges to a limit y. At the present moment, we cannot evaluate y directly. However, passing to the limit with respect to m in the above inequality, we obtain absolute value yn minus y less than or equal to 1 over 2 power n minus 1. Hence, we can calculate y to any desired accuracy by calculating the terms yn for sufficiently large n. The reader should do this and show that y is approximately equal to 0.632120559. The exact value of y is 1 minus 1 over e. And the next example is the sequence 1 over 1 plus 1 over 2 plus until 1 over n diverges. Let h equal hn be the sequence defined by hn equal 1 over 1 plus a half plus until 1 over n for n element n, which was considered in 3.3.3b. If m greater than n, then hm in hn equal 1 over n plus 1 plus until 1 over m. Since each of these m minus n terms exceeds 1 over m, then hm minus hn greater than m minus n over m equal 1 minus n over m. In particular, if m equal to n, we have h to n minus hn greater than a half. This shows that h is not a Cauchy sequence. Therefore, h is not a convergence sequence. In terms that will be introduced in section 3.7, we have just proved that the harmonic series sum of 1 over n from n equal 1 until infinity is divergent. And next is definition 3.5.7. We say that a sequence x equal xn of real numbers is not contractive if there exists a constant c, 0 less than c less than 1, such that the absolute value xn plus 2 minus xn plus 1 less than or equal c times absolute value xn plus 1 minus xn for all n element natural number. The number c is called the constant of the contractive sequence. And next is theorem 3.5.8. Every contractive sequence is a Cauchy sequence and therefore is convergent. Proof: if we successfully apply the dividing condition for a contractive sequence, we can work our way back to the beginning of the sequence as follows. Absolute value Sn plus 2 minus Xn plus 1 less than or equal to C times absolute value Sn plus 1 minus Xn less than or equal to C squared times absolute value Sn minus Xn minus 1 less than or equal C power 3 times absolute value Sn minus 1 minus Xn minus 2 less than or equal to until C power n times absolute value x2 minus x1. For m greater than n, we estimate absolute value as m minus Sn by first applying the triangle inequality and then using the formula for the sum of geometric progression C1.2.4f. This gives absolute value as m minus Xn less than or equal to absolute value xm minus xm minus 1 plus absolute value xm minus 1 minus xm minus 2 plus until absolute value xn plus 1 minus xn less than or equal to c power m minus 2 plus c power m minus 3 plus until c power n minus 1 times absolute value x2 minus x1 equal c power n minus 1 times 1 minus c power m minus n over 1 minus c times absolute value x2 minus x1 less than or equal to c power n minus 1 times 1 over 1 minus c times absolute value x2 minus x1. Since 0 less than c less than 1, we know limit c power n equal 0, c 3.1.11b. Therefore, we infer that Sn is a Cauchy sequence. It now follows from the Cauchy convergence criterion 3.5.5 that Sn is convergent sequence.
Example 3.5.9. We consider the sequence of Fibonacci fraction xn equal to fn over fn plus 1, where f1 equal to f2 equal to 1, and fn plus 1 equal to fn plus fn minus 1. See example 3.1.2.d. The first few terms are x1 equal to 1, x2 equal to 1 over 2, x3 equal to 2 over 3, x4 equal to 3 over 5, x5 equal to 5 over 8, and so on. It is shown that the sequence xn is given inductively by the equation xn plus 1 equal to 1 over 1 plus xn as follows. Xn plus 1 equal to fn plus 1 over fn plus 2 equal to fn plus 1 over fn plus 1 plus fn equal to 1 over 1 plus fn over fn plus 1 equal to 1 over 1 plus xn. An induction argument establishes xn greater than or equal to 1 over 2 less than or equal to 1 for all n, so that adding 1 and taking reciprocal gives us the inequality 1 over 2 less than or equal to 1 over 1 plus xn less than or equal to 2 over 3 for all n. It then follows that absolute value of xn plus 1 minus xn equal to absolute value of xn minus 1 over 1 plus xn times 1 plus xn minus 1 less than or equal to 2 over 3 times 2 over 3 times absolute value of xn minus 1 equal to 4 over 9 times absolute value of xn minus 1. Hence, the sequence xn is contractive and therefore converges by theorem 3.5.8. Passing to the limit x equal to limit xn, we obtain the equation x equal to 1 over 1 plus x, so that x satisfies the equation x squared plus x minus 1 equal to 0. The quadratic formula gives us the positive solution x equal to minus 1 plus square root of 5 over 2 equal to 0.618034 and so on. The reciprocal 1 over x equal to 1 plus square root of 5 over 2 equal to 1.618034 and so on is often denoted by the Greek letter P and referred to as the golden ratio in the history of geometry. In the artistic theory of ancient Greek philosophers, A rectangle have P as the ratio of the longer side to the shorter side is the rectangle most pleasing to the eye. The number also has many interesting mathematical properties. Next, 3.5.10 Corollary. If x equal to xn is a contractive sequence with constant c, and where c is greater than 0, less than 1, and if x star equal to limit x, then the first absolute value of x power star minus xn less than or equal to c power n minus 1 over 1 of minus c times absolute value of x2 minus x1, and the second absolute value of x power star minus xn less than or equal to c over 1 minus c times absolute value of xn minus xn minus 1. And this is the proof. From the preceding proof, if m greater than m, then absolute value of xm minus xn less than or equal to c power n minus 1 over 1 minus c times absolute value of x2 minus x1. If we let m approaches to infinitely in this inequality, we obtain the first corollary. To prove the second corollary, recall that if m greater than n, then absolute value of xm minus xn less than or equal to absolute value of xm minus 1 plus blah 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 until plus absolute value of xn plus 1 minus xn. Since it is readily established using induction that absolute value of xn plus k minus xn plus k minus 1 less than or equal to c power k times absolute value of xn minus 1. We infer that absolute value of xm minus xn less than or equal to c power m minus n plus blah 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 plus c power 2 plus c times absolute value of xn minus 1 less than or equal to c over 1 minus c absolute value of xn minus 1. We now let m approaches to infinitely in this inequality to obtain assertion corollary 2. Example 3.5.11. We are told that the cubic equation x power 3 minus 7x plus 2 equal to 0 has a solution between 0 and 1, and we wish to approximate the solution. This can be accomplished by means of iteration procedures as follows. We first rewrite the equation as x equal to x power 3 plus 2 over 7 and use this to define a sequence. We assign to x1 an arbitrary value between 0 and 1 and then define xn plus 1 equal to 1 over 2 times xn power 3 plus 2 for n element of natural number. Because x1 greater than 0 and less than 1, it follows that xn greater than 0 less than 1 for all n element of natural number. Moreover, we have absolute value of xn plus 2 minus xn plus 1 equal to 1 over 7 times xn plus 1 power 3 plus 2 minus 1 over 2 minus 1 over 7 times xn power 3 plus 2 equal to 1 over 7 times absolute value of xn plus 1 power 3 minus xn power 3 equal to 1 over 7 times absolute value of xn plus 1 square plus xn plus 1 times xn plus xn square times absolute value of xn plus 1 minus xn less than or equal to 3 over 7 times absolute value of xn plus 1 minus xn. Therefore, xn is a contractive sequence and hence there exists R such that limit xn equal to R. If we pass to the limit on both sides of the equality xn plus 1 equal to xn power 3 plus 2 over 7, we obtain R equal to R power 3 plus 2 over 7, and hence R power 3 minus 7R plus 2 equal to 0. Thus, R is a solution of the equation. We can approximate R by choosing x1 and calculating x2, x3 and so on successively. For example, if we take x1 equal to 0.5, we obtain 2 decimal place, x2 equal to 0.03571429 and so on. To estimate the accuracy, we note that absolute value of x2 minus x1 less than 0.2. Thus, after n step, it follows from corollary 3.5.10 in the first corollary that we are sure that absolute value of x power star minus xn less than or equal to 3 power n minus 1 times 7 power n minus 2 times 20. Thus, when n equal to 6, we are sure that absolute value of x power star minus x6 less than or equal to 3 power 5 over 7 power 4 times 20 equal to 20/3 per 4x020 less than 0.0051. Actually, the approximation is substantially better than this. In fact, since absolute value of x6 minus x5 less than 0.000005, it follows from corollary 3.5.10 in the second corollary that absolute value of x power star minus x6 less than or equal to 3/4 times absolute value of x6 minus x5 less than 0 times 0.0000004. Hence, the first 5 decimal places of x6 are correct. Okay, this is from group 10. We apologize if we have any mistake. Thank you for your attention.